So the last Greek that I want to go through the calculation of is theta. And so theta is the rate of change of the value of the portfolio with respect to time t. And again, our portfolio that we're considering just contains a single call option. So the price of our portfolio is going to be the Black-Scholes price for a European call option. And so we'll just start by taking the partial derivative of the Black-Scholes price formula with respect to t, and that's what we're going to call theta. And so here it's going to be a little bit more complicated, because now I have this e to the minus qt minus t. That term has a t in it. E to the minus r t minus t, that has a term in it. Has a t in it. Phi of d plus is a function of d plus, and d plus depends on t, and so does d minus. So I have to use the product rule on each term here. So what I'll get is the derivative of the first term. So here is where the minus signs cancel out that I confused myself with in the last set of slides. So here it's minus, I really should have done this with a substitution because I'm even confusing myself now. So what's going to happen, I have a minus sign here that's going to pop out in front, and a minus sign here that's going to also pop out in front. And I think maybe the easiest way to look at this is I have e to the minus q times capital T. That doesn't depend on little t. And then I have e to the minus q times minus t. So when I take the derivative, it's e to the qt that's kind of playing the important part of that. So I just get a q popping out in front. So it's q times t. And there really is no minus sign here. It's just because of the actual way the formula is written down that it looks like there's two minus signs. But with respect to the variable I'm taking the derivative of, it's e to the qt. So what I'm going to end up with is derivative of the first function times the second function plus derivative of the second function. So that's going to be the partial derivative with respect to t of phi of d plus times the first function. That's just the product rule. And then this subtraction is coming from here just because it's the first term minus the second term in the pricing formula. And then the same thing's going to happen. This really is e to the rt times e to the minus r capital T. So when I take the derivative, it's going to be just one little r that pops out. So I have derivative of the first term times the second term plus derivative of the second function times the first function. So it's just the product rule again on the second term of the pricing formula. And so now I'm going to look at this, and maybe we can squeeze just a little bit more mileage out of our kind of intermediate result. But what I want to do is, right now I have d minuses in the square brackets and d pluses in the first line. And that result ended up working out well when I had an s in one term and a k in the second term. So what I'm going to do is just rewrite these so that I have the two q's, no, which one's together? Plus, plus, minus, minus, p of dt. So I want to have the two functions that have the partial derivative with respect to t of the phi. Those will go in one group, and then the other two will go in the second group. So I end up with this expression here. And now I have this, no, it's this one that I can get rid of. So I have a way to replace this with something that depends on s, so actually something that's going to be equal to this again. So let's see. So here I'm just working on the part in the square brackets. So here I've used the chain rule. So the derivative with respect to t of capital phi of d plus, that's become lowercase phi of d plus, times partial d plus with respect to t. And then the same thing for the second term. The derivative with respect to t of capital phi has become lowercase phi of d minus times the partial of d minus with respect to t. And now I can do this same trick that I had done before. So I have now a partial derivative. So I can replace this guy here with this. That was that intermediate result that I had before. And so I can rewrite this bit in the square brackets like this. And now last time I had the derivative with respect to sigma. This time it's the derivative with respect to t, but I'm still going to have this d plus minus d minus, which is going to simplify that expression quite a bit. So I'm going to look at this quantity in a little bit closer detail. So I can rewrite that again as the partial derivative with respect to t, just of d plus minus d minus. And so in light gray here, I tend to confuse myself if I try to take a derivative of something with a square root, just like when I have a rational function. If I have 1 over sigma, I'd rather write that as sigma to the minus 1. Here I have square root of t minus t. I'd rather write that as the quantity t minus t to the 1/2. And so now I'm set up to use the power rule to take the derivative here. So what I'm going to end up with, I have 1/2. So that's where this 2 comes from. Then I'll have the quantity t minus t to the negative 1/2. That's going to be where the 1 over square root of t minus t comes from. And then I have this sigma left over in front, and that's where the sigma in the top comes from. And then by the chain rule, so the derivative that I'm taking here is with respect to t, and in the inside function, t is negative. So I have to multiply this by -1 by the chain rule. So if I'd made a u substitution and said u is equal to capital T minus little t, then when I took the derivative of u, I would get -1. And so this is the expression for theta that I had before. So it's the second term that I'm going to be able to simplify using my trick. And I now have an expression for this here, which is just minus sigma divided by 2 times the square root of t minus t. And so that's going to finally give me my expression for theta. So this one, unfortunately, doesn't simplify much further than this. And so all I've done is just substitute the expression we had last time into the first term here, and then left the other 2 terms alone.